Hello, everyone. Today I will present the article titled Distributed Algorithms for Boolean Equations over Network. So, this work was published in IEEE Transactions on Automatic Control in November 2023 and provides a fascinating approach to solving Boolean equations in a distributed way, ensuring privacy and scalability. So let's start with the introduction of it. Yeah. So these equations involve values that are either true and false, like it actually represented as 1 or 0. So they are used in many areas like gene regulation in biology, securing communication in cryptography, and tracking epidemics in computer networks, and lastly, the making economics decisions. So I will give the example of it that how the author worked on the problem. So here it is. Imagine a group of students they are they are trying to plan a secret party. So excuse me. So each student has a personal condition, like it must be like one student will say that it must be on Friday, or the second will say it must be after 6 p.m. So these two are their conditions, but they are secrets of them. I mean, they are not telling directly to anyone. So they want to find a time that satisfies everyone's rules, but they don't want to reveal their conditions to other. So this is similar to the problem tackled in this article, where nodes in a network have private Boolean equations and need to solve them collectively without sharing their private information. And let's go to the problem statement. So the main problem here is that each node in a network has its own private Boolean equation, and all nodes want to solve the entire system collaboratively. So the key challenges include local privacy, where their nodes cannot share their equations directly. And second is the distributed computation, where the solution must be computed across the network without a central controller. And third is the scalability. The system should handle a large number of nodes efficiently. And the fourth one is the computational overhead, which minimizing the data exchange to avoid delays or leaks. And in mathematical terms, we represent this problem as where the maps Boolean variables to a true or false outcome. So here it is the key contributions. So the main challenges faced in the solving this problem are local privacy, which ensure that nodes do not reveal their equations or their solutions. So second is high complexity, where the Boolean equations are often NP-complete problems, and in scalability, as the network grows, computational and communication costs increase significantly. If I give the example, so in the party planning analogy, if 100 students each have different rules, it becomes extremely difficult to coordinate and to find a solution while keeping everyone's preferences private. Here's the thing, so that's why. So let's go to the proposed solution, where the author proposes the solution that combines five key algorithms to address these challenges. So the first algorithm is Boolean metricization, which converts the Boolean equations into a form that can be solved by using linear algebra. And second is the distributed linear algebra solver, which solves these linear equations distributedly using a projection consensus algorithm. And the Boolean vector search, it maps the linear solutions that back into the Boolean solutions actually. So the fourth one is the distributed set verification, where it checks if the system of Boolean equation is solvable before proceeding or not. So the last one is differential privacy extensions, where it ensures that computations remain private by adding controlled noise. Next slide, methodology. So the overview of methodology is that I explained each and every algorithm step by step. So let's start with the Boolean metricization. So the first step is transforming each Boolean equation into a matrix form. For example, if a node has the equation, it can be converted into a linear form, like where it represents the matrix equivalent of the Boolean equation, where it is the solution in the transformed space, or it encodes the Boolean outcomes as a vector. So next, distributed linear algebra. Once transformed, the linear equations are solved distributedly. Nodes use the projection consensus algorithm, where they iteratively update their states based on information from their neighbors. This ensures that the conversions of to a shared solution without revealing private data. Third one is Boolean vector search, the solution obtained from step two, where it is in the linear space. This step searches for valid Boolean vectors in the affine subspace, which in converting the linear solutions back to the original Boolean format, like decoding. So the fourth one is the distributed set verification. So before solving, the system verifies whether a solution exists or not. If the Boolean equations are unsolvable, the algorithm terminates early, and it saves the computational resources. And in the fifth step, which is the differential privacy extensions, in this it maintain the privacy. It controlled noise. When it added to the shared data during computations, and it this ensures no private information can be inferred, even if an attacker intercepts the communication. So it is safe for every interception or every attack. So the findings, the result of the article, it proposed that the algorithms yield the following results, which are correctness. In correctness, there are the algorithms find the exact solution with high probability. Uh, and obviously, it was working for the privacy also, where the differential privacy ensures nodes data remains secure. And the third one is scalability. While the effective and the approach has challenges, the scaling to extremely large networks. So suppose the network has two equations that are at least one of many is the true or false. So the algorithms transform these equations, solve them collaboratively, and return solutions. So the recommendation and critique are first, let's start with the recommendations. So if the, I mean, apply, it should be the apply these algorithms in fields like distributed control systems, where the secure voting and collaborative robotics are there. And second would be to explore ways to improve scalability and using parallelization or advanced optimization. These both are the recommendation from my side. And the critique is the computational and communication costs remain high for a very large system. It is the worst case, which should be, overcome. The second would be the methods complexity might limit practical applications in resource constrained networks. So yeah, these two are the uh, points which it should be, I mean, working on in future. So lastly, my personal view on this are uh, this, I mean, in my opinion, this work is a strong step forward, I mean, in privacy preserving distributed computational. The integration of linear algebra and Boolean logic is innovative, and the use of differential privacy is a valuable addition, I would say. However, I mean, reducing the complexity and improving scalability would make it more better, more impactful. And if we say if we take the real world analogy, which is the distributed voting system, where each voter keep their preferences private, but collectively determines the election result without exposing individual votes. So that would be the main example of this problem in the larger scale, I would say. So to conclude the article presents a novel method for solving Boolean equations in a distributed, privacy preserving manner. And the algorithms are effective and secure, but scalability and computational costs remain areas for improvement, where I mentioned above. And in future, for the future one, I would suggest that not it's not a suggestion, but it could be future research should, I mean, focus on optimizing these aspects to enable broader real-world applications that I mentioned above. So yeah, that was the presentation. Yeah, these two are the questions with their answer for the final exams, and it is the last. Yeah, thank you so much uh, for for your attention. Yeah, thank you.